sorry, I have 2 other things to do in different building. When you will leave this building afternoon or in noon, you have to go that side, and at the end of this road, and there are the computers already. I saw it. There is a problem set. I saw it. No, I didn't solve problem set. So good luck and see you. If you need something, don't call me. Don't touch anything. Thank you.
Okay, thank you, Boba. I think we are just waiting for a few people to arrive, but when I arrived here, I was thinking, you know, when I was a student like yourself, Saturday morning, early morning lectures, we all hated it, but at the same time, after many years, we all loved it because it's such good memories, you know? You get out early in the morning, you have a nice coffee, and we have a very nice coffee today. I'll just tell you in a second where you can find it. And after many years, it's really good memories. So I was feeling, you know, I'm coming to the university Saturday morning, and luckily, as Boba said, I'm not here, and we are not here to teach you anything because you already know so much. But we want to share with you, I want to share with you some general numbers about the ICPC community. I'll go very fast because I think some of you may have seen my slides, so I will not spend much time. Oh, it's not working. No problem, no problem. So I don't have to explain you what is the ICPC, but maybe it's a surprise for you that it has been founded in 1970s. And the founder of the ICPC, Professor Bill Poucher, you've all met him yesterday, so take this opportunity, take a selfie, come and say hi, and Bill is one of the kindest and one of the most open persons that I've personally met, and he will always be very happy to spend some time with you. Okay, so we have more than 100 countries participating. We have more than 4,000 universities participating globally. This is the spread across the regions. And we are now here today in the European super region. I think many numbers have been shared yesterday about the Europe specifically, but it's a general overview. So those of you who will advance to the World Finals will meet teams from all of these super regions, right? So get ready for that. And this is the map of our World Finals locations. As you know, it moves every year, right? And this year, just in a couple of weeks, we're all heading to Egypt. And I think some of you may be there as well, because we're catching up with 2 previous post-COVID years. But your World Finals location will be in Kazakhstan, as it has been shared. A very beautiful, fast-growing country. So I'll not spend much time here. This is the current world champion, MIT team. And actually, they won last year at the North America Championship. And then they became the world finalists. So maybe I hope to see some of the teams becoming champions here and becoming the world finalists. I wish you that. That's an interesting slide that we did a short survey of more than 30,000 alumni. You know, you will be an alumni in just a few months after competing in the ICPC. And we just try to find out what do they do as a job so that we can also find something interesting and bring this, potential future employees for you right here at the competition. So actually, as you can see, the majority of this sample of 30,000, they are taking engineering jobs, right? No surprise. But there is a good portion going into research and development. And some of them are even becoming founders of their own startups, founders or co-founders. I'm just sharing, it's purposely written in a very small letters because that's the global top 200 employees. And actually, you can meet some of them right here on the first floor. So I would really encourage you to take your time, go and talk to every single sponsor, even if you are not considering this opportunity for you right now. You never know where and how you will meet them, and maybe it could be a good opportunity also for your friends. So we have, and I'll introduce each sponsor one by one, but we have amazing opportunities here, and they are also open for your friends. So take some time after these tech talks. We will be serving snacks. Also, Huawei is making an amazing coffee. And some other sponsors also prepared some nice snacks for you. So take your time, go to the first floor and say hi to everyone, right? No obligation, but it's about community building, networking, making new friends, and also making your professional career and professional contacts. Here are some of them, and maybe across this room, you will also meet the future founders of like top engineering companies, like the first employee of Google, Craig Silverstein. He was the world champion in 1993. Adam D'Angelo, the CTO of Facebook. And for example, this year in Kazakhstan, we will have Jacob Pachonsky, who is not far from here, who is originally from Poland, and he is the chief researcher at OpenAI ChatGPT. So he was also competing at the World Finals some years ago, and now he is doing the research at the OpenAI, and he will be sharing like how ICPC career helped him and what he's doing right now in his company. So I'll not spend much time on this slide. I'll see some of you in Egypt and hopefully more of you in Kazakhstan, okay? And as I'm here, basically my role in the foundation, I'm helping with the development of new initiatives and new projects, new initiatives like alumni initiatives or training camps or special initiatives for girls. By the way, I would highly require each and every one, once you go back, please share this news about this competition with at least one girl at your university. First of all, it will allow us to have more girls competing in the upcoming years. But second, it's always a very nice way to meet and talk to a girl at your university. So don't miss this chance. Talk at least to one girl at your university once you're back. Okay, and now I see you're quite awake. We have some very interesting talks for you. And again, when we are doing the talks in the ICPC, we always want to make sure that this content is relevant to what you are studying right now, what you are doing right now, and something that can open up new topics and new opportunities for you in the future. So you'll not hear any like marketing talks or like advertisement. So we really worked hard with our sponsors to make sure that the content is relevant for you. So we will have the talk on the research field, right, in a few seconds from Huawei. And we will have the ICPC champion, Pavel from JetBrains, who will also share some fun stuff about his experience. I'll not give more details and delay, but I just want to give an introduction of every single company just in a glance so that you have an idea, and when you go and talk to the companies, you understand what are they doing, right? JetBrains probably doesn't need much introduction because many of you are using their tools, right? And they are our global tool sponsor. And also they actually have a dedicated page that helps you to prepare for the future competitions and boost your results. And make sure to stop by, and they will share with you where these training materials and some nice tools for the competitions can be found. Huawei, it's our multi-regional diamond sponsor. And as you know, it's a leading provider of information and communication technology infrastructure and smart devices. They have offices in more than 170 countries. And those of you who are interested in international career opportunities and especially in research opportunities, I would highly encourage you to talk to them because right across Europe they have more than 20 research centers and they have nice international internship opportunities in Hong Kong, in China, or basically all over the world, 170 countries. And also they have been sponsoring the ICPC challenges. As it was mentioned yesterday, it's a very big task actually for the industry to prepare a problem. And how it works, the industry is taking real problems from the fields where they are working. And we're working together trying to make sure that it's fitting the format of the competitions that you are used to, that is fitting the format of this, criteria for the judges. And that's the way for you not only to compete and basically train, it's also the way for you to learn new skills that are applied skills from the industry. And needless to say that there are some amazing prizes. And even there is one way actually to get to the World Finals without being the current ICPC participants because some special prizes of these challenges include the trip to the World Finals in a volunteer role. So if you win this challenge in the future years, you may have a chance to come to the World Finals as a guest, not as a competitor. Some new sponsors that we have. I know many of you are familiar with finance industry, and we have two companies from finance. They're very different. Many of you know Jane Street. Jane Street is our Europe regional sponsor, and it's a quantitative trading firm with offices worldwide. They have a lot of opportunities in exploring software engineering, quantitative trading, quantitative research, and they are now open for summer internships. So Jane Street will be here starting from 10 a.m. Just stop by and say hi. All the sponsors are on the first floor. They have really nice opportunities and offices. And those of you who are interested in finance, that's a nice company of your choice. And last but not the least, finally, they are from the same industry. I have to share, it's an interesting story of the company. One of their founders, he was the world finalist in the ICPC. It's a small, basically it's more like a startup company, but super successful. So it's also in finance. It's a privately owned and funded algorithmic trading firm. And basically, they have a team of mathematicians, programmers, engineers, and they are maintaining the structure like in the ICPC family style. So it's also a finance firm, but different style. So I would really encourage you to talk to all of them and find out some nice opportunities for you and for your friends. Thank you. In case you have any questions, I will be here around with you today and tomorrow. Just stop by, say hi. I'm happy to meet all of you. Yeah? And now let me welcome our next speaker. Okay. I would like to introduce Maciej Maciejewski. Sorry if I'm misspelling your name. Okay. Okay, so Maciej is coming from Huawei Research Center, and he is leading the entire department focused on product line, right? Not product line?
It's on
well,
memory subsystem.
On memory subsystem. So the topic of the talk is May You Live in Interesting Times, and Data Center Hardware Progression and Memory Subsystems. Sounds quite complicated to me, but I'm sure it's one of the easy problems you can solve. So welcome, everyone. Yeah, have fun. So we'll have a short talk from Huawei, short talk from the world finalists, from JetBrains, and then we're waiting for you for snacks on the first floor. Yeah. Enjoy your day.
Thank you. By the way, how many minutes I have? Because I can spend the entire day here. Okay, I'll spend just the entire day. Oh, you can see my screen. Great. Okay, thank you for the introduction. I'm focusing on the research in the memory subsystem for the data centers, where the situation is quite dynamic. Like many years ago, it was very simple, which I will show on later, but right now we are dealing with the heterogeneous memory hierarchy, different subsystems that we have, so it's getting really very complex. And from this perspective, it's not the only thing that you can do software that adapts to it, do the middleware layer and so on. You need really cooperation with the many research teams, and this is what we are doing. I wouldn't say mainly, but it's a big portion of our work is cooperation with academia. So we have a couple of active collaboration with different professors in completely different fields, just to augment the future, the way how future software will look like. And I'm by education electronics engineer, optoelectronics. So I'm not software, I'm not the ICPC guy, but in my life I've spent like my entire professional career in software development. So it's not a problem if you're in the different background. Software is easy, right? To some extent. If you exclude math, it's getting easy. Being the ICPC champion is actually very beneficial. I have in my team currently silver medalist from the World ICPC, and he's leading one of the teams and is actually doing a great job in understanding the problem and working towards the solutions. Okay, with that we can start. We have also a couple of prizes, and I will have a couple of questions to you. And let me start by focusing on the environment. So we are, my team is working on data center software. So it's not for wearables, it's not for entertainment, it's for data centers. So actually where the big data is going, all the calculations, AI and so on. And this is the example of a church-located data center. So churches are apparently in Europe popular for the computing stuff. This is a Barcelona supercomputer, Mare Nostrum. So some of you I've seen yesterday from UPC, they've probably been over there. It's a really very nice location. So if you're in Barcelona, I highly recommend it. But with that, I have a couple of questions like on the data center. So as you can imagine, this is like rows of racks, plenty of servers. Each rack has like 20, 40 servers, depends on whether it's medium density, high density, plenty of different aspects. But when you are owning your own company, your own Google, and you want to deploy another data center, what are the factors that you would take into account? You have to take into account. Any guesses? And please raise your hands. Yes? Power delivery, yes, exactly. Can we have a prize over there? Oh, thank you. So, no, don't clap, it's too many clapping. So power delivery in terms of how much power you need to have. So what is the typical size of the power requirement for the data center? Anyone? How the scaling works? So, kilowatts or some different numbers? Yes? Gigawatt? No. No prize for you. Any other guesses? Yeah, exactly. Man in the yellow shirt, please. So the typical scaling is at least a couple of megawatts, but like the big ones take just a factor multiplication of 10 megawatts and deploy like, okay. If we have a power line that can supply us with 50 megawatts, we will just place 50 megawatts over there. It's not a problem. The main limitation actually is the power supply. Any other guesses on the factors to choose the data center? Yes? Cooling. Now it's a factor for the power. So when you have 50 megawatts power, half of it you need to spend for cooling. It doesn't matter if it's like cold climate, warm. It's negligible. Yes, up there? Can you speak louder a bit? I can't hear.
Risk management. You don't want your data center to get flooded, for example.
Exactly. Natural risk management, so volcano eruptions, earthquakes. Also government stability is a big issue for the risk management. Anything else? Yeah, we can, the man in the green shirt, please. Internet speed, it's actually a connectivity. So how close you are to a major hub of fibers that go under the ocean and so on. Yep. Okay, any other guesses? Or are we done? Not really. Like if you have, so the answer is space. If you have a availability of the power resources, usually you don't care to have a data center in the city center. You can do it in the rural area, and the space is always available. Yeah? Scalability, not really. Like you're just putting anything there, and if you have more power, you will just buy more land or go somewhere else. Okay, last one.
Maybe just generic cost of rent or
Yes and no. Cost of power, yes. Cost of land, no. And the last one I would say is also geographic location in terms of you want to be close to your users. So if you have all the data centers in the US, for example, you will have poor connectivity to Asia or Europe. So general location. Okay, let's proceed to the more technical stuff. As you might be aware from the prehistorical times, like we have von Neumann architecture for the computing, which is the processing unit, you have the storage, and control unit, which is basically the CPU, and it's pretty much unchanged from this time. And what we have right now, every one of you is probably using Linux in the daily work, or not really work, the education or the competition, which is very old operating system. And we see actually right now very nice initiatives to replace it, and there are new operating systems that are coming to life, like DBOS, aimed at the distributed databases and supporting them. But anyways, like in the 90s, early 2000, the world was very simple. This is pretty much where I was doing my first steps in the professional life. We had pretty much one vendor of the CPUs, then regular hard drives, nothing else really, and simple DRAM. No problem with writing any software. But if we look at the current times, so since like 10 years we have a boom because we've seen that the scaling of those CPUs or memory subsystem is not following up with the workloads that we need to do. Like AI is pushing to the limits whatever we have right now even. If you look at the requests for how many GPUs people want to buy, for example. So what we can see on the software side, we have virtualization, which is already like a boomer thing. We have containers and other function as a service activities, plenty of those. On the storage side, not many things has changed. So we have faster drives, we have different protocols, attachment protocols like NVMe, PCIe, bus. Then we have medium, which is either QLC, like quad cell, TLC, and so on. So a bit of progress over here, but in general, the speed is still relatively low. It's in the tens of microseconds for access. On the CPU side, however, there is a huge change. So beside of the regular x86 architecture, we have ARM architecture that is coming to life very well, like from, for example, Apple CPUs, Huawei CPUs. Those are actually ARM architecture. And there is also RISC architecture that is coming to life and probably will be a big thing in the coming years. On top of it, we have GPUs, for example. We have the NPUs, TPUs, which are like basically FPGAs or ASICs that you put next to any logical place in the system. Like, for example, if you have an NPU, which is the network processing unit, or SmartNIC, some say, you have network interfaces and some FPGA that you can program to accelerate your networking functions like compression, for example, or encryption of what is going to the network. The similar, this is actually quite old product from Google, the TPU, Tensor Processing Unit, which is aiming only at giving you the extra speed on tensor processing. In my eyes, because this is my area, the most interesting things are happening in the memory ecosystem, where from regular DRAM, regular DRAM is over here, we have seen the shift to having multiple different products. So first we've seen on the market was the HBM, which is high bandwidth memory. This is basically a stacked DRAM that is placed on the CPU and is aiming to give you the higher bandwidth than the regular DRAM for the workloads that are actually needed. And if anyone is able to tell me more or less what is this bandwidth, the high bandwidth? What kind of bandwidth we're talking about? Yes? Terabyte? You said terabyte? A bit overshoot. Another one? Gigabyte. No. So maybe let's start from a simple question. What is the bandwidth for the regular DRAM? Like DRAM subsystem, entire for the, let's say you have a socket and you have 6, 8 modules, DRAM modules connected to it. Yeah? Yeah, around 100 gigabytes per second. Yeah, that's a good answer, but you already have a scale, right? So no more for you. Yeah?
I have important message from Boba. Is there someone from Czech Technical University team? Can you stand up, please? No. Okay, thank you very much.
No locals. No wonder. They have comfortable beds at this hour. Okay, so once we establish that DRAM is 100 gigabits and 1 gigabytes per second, and 1 terabyte is too much, so what is the scaling factor, more or less? Anyone? Oh, you're all asleep. Yes? It's like not gigabits, it's gigabytes actually, and it's like 400 gigabytes. Okay, let's applaud the guest, closest guest. Okay, so we have HBM, which is delivering, in theory, around 400 gigabytes per second. In practice, it's nowhere near, right? If you have a benchmark, you have idle memory, you can get this 400 gigabytes per second, maybe. But once you actually start using it, in real life, it goes down to like maybe 120, not more. And same with DRAM. Once you are starting to use it, it drops down from 100 to like 60. Then the most interesting stuff is processing in memory, which means like this is a new, let's say, electronics technology where we have possibility to embed arithmetic function within the memory cells. So when you like read a particular row, you are getting already the multiplication of like 2 above rows, something like this. And there are multiple functions that you can embed, and it's speeding up computation vastly, as you can imagine, because you don't need to get the data to the CPU, calculate, you simply get a request to the memory and you get a response immediately. So approaches like processing in memory, processing near memory are currently in the heavy research, and they will come to life in the coming decade, I would say. And then from the material science, regular DRAM is a transistor-based memory, and we are having a different approach that actually was already on the market. Intel released it for like 2-3 years, then backed up from it, but it will come back very soon. And this is the phase change memory, which is basically a material which is a crystal or amorphic, and it depends on how you push it to the temperature. So if you are slowly warming it up, it gets crystalline, and if you are pushing a big peak of temperature, like through current, it gets amorphic. And you can read the resistance of it and therefore see if it's like 0 or 1, or actually you can do more things with it. So as you can see, everything is getting really complex over here. From the memory subsystem, why this is getting complex? Because we see the walls, like the progress in material is not following the progress of the computation. So the CPU computations and adding GPU and those other processing units require way more speed, way more bandwidth from the memory than the memory is able to give. And this gap of the technology progress is actually growing. And it grows by 50% a year. So we are getting more and more choked by the memory. And by the way, on the right-hand side, you can see the same from the networking ecosystem. So network lines, like those 100 gigabit interfaces, 400 gigabit interfaces are not enough right? And there is no clear path to actually help in both of those areas. Yeah. You can see a nice thing over here, maybe just to give you some technical details. This is the latency of the memory translated to already the computations that were done with access to the memory. And theoretically, like this is the idle memory. So if you are just, no one is using the memory subsystem, you're getting the data, doing computation, you get a line like this. But when you are having a loaded system, you see the difference in the performance and its logarithmic scale. So it's like really a thing to consider. Another factor for the memory ecosystem is the power that we should consider. Not many people do, because there are other components in the system that draw a lot of power, so it's very tough topic to optimize anything with it. But the power drawn by the data centers is growing, and with the AI, it's growing even faster than predicted over here, I believe. But differences in the power consumptions are quite vast. Like, you have internals of the CPU, like very simplified over here. And when they are doing the simple calculations with the CPU, the power to get the data from the registers and do the computation is relatively small. So those are picojoules. But once you have to go to the cache subsystem, it's still okay. So cache subsystem is maybe like twice, 3 times more expensive in terms of power. But once you have to go to the DRAM to get the data, it's getting to the nanojoules level. So it's 1,000 times more power consuming to get the data from DRAM than to process it with the cache subsystem. Yeah. Another factor that is getting our life more complex is general design of the computers, of the servers. So we have a picture over here with the 8-socket server, which is actually a big one. Typically you see 2-socket servers, sometimes 4-socket, but this is the 8-socket, which is mainly used through for some big, not really a big data, so big databases, guys, that cannot scale the software very well, old software, so they just take more CPUs to do a better job. But even with a typical 2-socket system, oh, by the way, one more question that came to my mind. Do you know, like, any guess that why 2-socket system, like when you have one node and it has 2 CPUs, why the number 2 is like the most popular in the world? Not 1-socket system, not 4-socket system, but 2. Any guesses? No?
I guess the price, if we consider the price as a function of the number of sockets, you can consider it to be complex, and 2 is where the maximum, where it's most to our interest to actually have 2 and save on money, I guess.
Close, a bit around, but yeah, well, let's give out a price, why not? So the main factor is a form factor. Like when you have a rack which is 19 inches, typically, and you have 1U blade, which is like this size, maybe 5 centimeters, you can actually put inside 2 CPUs, you have place for it. So if you have place, you want to maximize the space that you get out of your rack. That's the main point here. But it brings complexity. Like over here, you can see when we are reading from a local registry, when we are computing, like the CPU works at 3 terahertz, 3 gigahertz right now, more or less, which means that the registry needs to be read within less than a nanosecond. Typical access to the caching subsystem is around 20, 30, 40 nanoseconds. when you go to the DRAM, it's already 100 nanoseconds. When you go to the remote node, like you need to hop between the sockets and get to the memory which is on the other socket, because, for example, you run out of your local one, you're adding an additional at least 100 nanoseconds. It depends on the CPU design and the interconnect design. It might be even 200 that you add. If you need to do the 2 hops, you get another one. If you're working with this lower medium, like this phase change memory, you get around 400 nanoseconds for reads. And interestingly, it's asymmetric. DRAM is symmetric. Caches are symmetric. This medium is not. It has like 300-400 nanoseconds for reads and around 600-700 nanoseconds for writes, which needs to be taken into account also in characterizing your workloads and deciding on which medium you want to position your objects. And if you go to the network, you're basically outside of the comfort zone of application to use efficiently. One last question. I think I've said it already. What is another factor that you need to take into account if you are trying to use remote memory? So you're operating, you have a process that is running on this CPU, and you are trying to use this memory actively. What other mechanisms you need to take into account?
Physical distance from CPU to memory, because it takes a few nanoseconds. If it's like 1 meter away from CPU, it will take a few nanoseconds to secure that.
Might be, but that's not a limiting factor. Plus, your Huawei will not give you a scale. Yes?
Maybe you take some CPU time of the intermediate CPUs?
Yes, you are, but not really the CPU time. Yeah, do we have like 2 more prizes? Okay. So that's a good point. You're not really using the CPU time, like the core time. You're using the uncore time. So the uncore caching subsystem needs to route the traffic and keep aware of it. Yes? Exactly, that's the point. Like the last one. Yes, too. So the consistency. You need to be aware, like each of the CPU needs to be aware how the memory is used, and it has ownership of its own local memory. It has to then keep track on which CPU is using it actively. There are like protocols like MESI, MOESI that are giving additional bits on whether marking whether the memory, like the cache line, is modified, it's shared, and so on. And you need a synchronization protocol running over here, which is either the snooping, so you're polling for each time, or there's a directory bits that you are setting to indicate ownership. And this is additional overhead that you need to do. Okay, just as a conclusion, because yeah, I guess I'm out of time vastly. So to deal with those memory complexity, there is no clear way to do it. Like, because CPU has no knowledge what kind of memory is attached. It has no interest even to know it. Applications, there is no company in the world that wants to modify their application to deal with the specific hardware. Like, I tried it with many companies and it doesn't work. Simply, kernel, it also has to be abstract enough and doesn't have enough of power to deal with all those complexities and difference in the characteristics of the memory. Kubernetes, like those upper systems, are actually quite interesting. Like you can embed plenty of logic into the scheduling. But still, this will be like very high level. Like you can do much more on the application level when you are modifying each and every object and deciding where it should sit, rather than looking at the pages, which are like 4K or 2 megabyte pages, and you are shifting the 2 megs data from this or that side. And there is a specialized middleware that probably is the way that everyone will end up in even a decade, where we have, for example, my team is working on the tiered allocator. So this is just taking a regular allocator like JMalloc and building a tiering layer on top of it that understands the memory complexity and is able to intercept the object creation. So we are just intercepting every new and malloc call and keeping track on the usage of the object. So like CPU counters, you monitor and you build a hotness table for each object type, and you are able to decide where to position the current object, the future objects, and so on. But this is a long process, so software development is not as simple as one can imagine. There's plenty of use cases that need to be considered, plenty of test cases, and the more importantly is that market adoption is really slow. Like when someone has something deployed, the ability and willingness to change is not as fast as market evolves. And once we are done, it's usually that there is like more different hardware that we need to adopt to, and there are different memory technologies that we see that will come very soon. And also from the memory perspective, if we plot neuromorphic or quantum computing, it changes completely how we deal with memory. So it makes our work, let's say, stable. So it's very ever-changing environment that we need to adapt to. But AI, I believe, will never replace with us with it, because it's way too complex and way too demanding. And with that, thank you so much.
Thank you so much. I've learned a lot of new things about the memory. And I encourage all of you to stop by and say hi to Maciej and to Huawei team on the first floor. And I've just tested for you the Huawei coffee. Just now they were hitting the machine and it's just excellent. So don't miss that. And now, without further delay, let me please invite the Pavel from JetBrains, the ICPC champion. And as you know, we don't have any former champions. So Pavel is the current champion, and I'm really looking eagerly to the talk. And the topic of Pavel's talk will be the fun stories and practical tips from the ICPC World Champion. So hopefully, again, I will see some of you on this same stage in a few years, given sharing your fun experience and tips with the future participants. So Pavel, thank you for joining us. And the floor is yours.
Hello, everyone. So the lecture is called Fun Stories and Practical Tips. And when I prepared it, I actually wanted to share some fun stories, but after I prepared it, it doesn't look very fun, actually, but we'll see. So we'll start with fun stories. They're not that fun as you may expect it, like fun stories, but they're more like enlightening stories, I would say. So these are some stories from my contest experience again, I started programming contests when I was in middle school, so it was like 30 years ago, so it was a long time ago. So I had some stories, and I picked just two of them. Okay. So the first one is from Google Code Jam 2010. If you remember this competition, it was like 14 years ago. And the story is not about how I won this competition, because I didn't win this competition. Actually, yes, Igor won this competition. We have a winner of the competition. It was before Gennadi's era, so you actually can win Google Code Jam at that time. The story is not about how I win this competition. Story about how I advanced to this competition, because it was actually challenging for me to advance to the World Finals. And I won't tell you about round 2 and problem bacteria in this competition. I'm sorry about this story. It will be a long story, and I need to explain you the problem. Okay, but you all are competitive programmers. You love problems. You like okay. So let's talk about problem bacteria. So problem bacteria look like this. You have any time will left until all the cells became dead. So you have some initial configuration. Initial configuration looks like this. So you have some set of rectangles. So initial configuration is like union of all these rectangles. And from this initial configuration, you need to count how many steps will this system live until every cell will be dead. Yeah? Okay, it's kind of like this. Okay, briefly, that's the problem. Very nice problem, actually. So what is the solution for this problem? So if you look at this picture, actually, you may have some idea of what's going on. So if you look how cells are dying, so they're dying in like diagonal fashion. So they are dying like diagonal by diagonal from left top corner to bottom right corner like this. And it's actually true for it turns out it's actually true for every connected shape. So if you take any connected shape, you can prove it stays connected after every transformation. So if you look at any connected shape, you may easily calculate the lifetime of this connected shape. So it will start dying from this top left diagonal. So you can find this place, and it will end dying in the top or in the bottom right corner of the bounding box. Yeah? So you find this point, the difference of these 2 points will be your lifetime of this shape, and then you just split everything in connected components. For every connected components you find its lifetime, find the maximum, ta-da, that's your solution. Yeah? Kind of get it, yeah? Okay, so this is very, very clever, very nice solution for very nice and beautiful problem. Unfortunately, I wasn't that clever that day, so it happens. So I have no idea how to solve this problem, but I have 2 hours left for the competition. So what I've done instead, I simply simulate the whole process. So what I've done instead, I split my grid. So I compressed all the coordinates. So you build this uneven grid when every rectangle is either filled with bacteria or is empty. Yeah? So every rectangle is completely alive or completely dead, something like this. Yeah? And then I try to simulate the whole process. Well, how to simulate the process? No, if you look at every rectangle, so the life of each rectangle is very simple, actually. So if you look at it, what will happen to rectangle? So you have some waves of these cells. So if the top left cell became alive, then at some point all the cells became alive like this. You have this wave of alive cells. And then the top left cell became dead, then you have like wave of the dead cells. So basically, to know what happened to any cell of this rectangle, you need to look at one cell. For example, if you look at the top left cell of the rectangle, and you remember all the events, so this is like lifetime of this cell. So if you know this if you remember these events when you change the state of this cell, you can deduce the lifetime of any cell. So any other cell of the same rectangle have the same basically life, but with some delay. Yeah, and this delay is like Manhattan distance. Yeah, like this. Yeah. So that's what you can do. So for every rectangle, I produced this sequence of events, basically. And then you can build sequence of events for a rectangle by knowing rectangles on top and on the left. So when you want to build sequence of events for this cell C, you build sequence of events for cells A and B, and then use kind of 2 pointers method. So you need all these events. Find all the points when you have 2 alive cells, when you have 2 alive cells, when you have a alive set here. When you have 2 dead cells, then you have dead cell here. So you make 2 pointers method, look like merging 2 sorted arrays. Okay. So you merge this arrays, produce this sequence, and so on. So, okay. This was brief explanation of my solution. Okay, I don't expect you to follow it completely with all details. I just want to show you that my solution is much, much harder than the intended solution. But it worked. Good. So basically what I've done in this problem, instead of taking a precision screwdriver and open the problem, I took my biggest hammer and just smashed it to the ground. And sometimes it works. So my first advice from this tip is sometimes it's okay to use a hammer. So if you believe you can solve the problem using the tools you have, just do it. So sometimes Sometimes you have a problem that, like, you see that half of the teams from the contest solve this problem. So, but you know how to solve the problem using, like, I don't know, persistent trips. If you know how to solve using persistent trips, you're confident you can do it. No, just do it. Okay, maybe your solution is not the easiest solution for this problem, but if you're confident enough, you can implement it and it will work. Okay, do it. Okay. Another thing, another thought in the same direction is that in this competition, the rules are so your solution considered correct if it passes all the tests in a given time limit. That's all what's important. Nobody cares what's inside the solution. So if your solution manages to solve all the tests in given time limit, it's fine. Nobody cares how you did it. Okay. Good. So that's the first problem. That's the first story from the lecture. So second story is actually much shorter. For the second story, we need to go to Google Code Jam 2018. So both my stories about Google Code Jam. It's very sad they shut down this competition. I'm glad. Obviously Gennady won this competition, so it's so again, this story is not about how I won this competition, how I advanced the competition. And the story how I advanced to World Finals in 2018 is actually like this. So they had, in round 3, they had 4 problems like this. So first problem is very simple problem. I don't remember the statement actually. Second is kind of some kind of constructive graph problem. So you need to do something to do something. So it looks like normal graph problem. It's actually it's mathematical problems. So. And then we have problems C and D, and these are 2 geometry problems. Okay. Who hate geometry problems as much as I do? Okay. I personally hate geometry problems. But we have 2 of them in 4 problem contests. And they are the most expensive problems. So what I've done instead, so you have very safe option. You go problem B. Problem B look like nice graph problem. Okay, problem A is easy. Everybody solve problem A very fast. Okay. So you have 2 options. You can go to very nice graph problems, or you can go to very scary-looking geometry problems. What would you do in this situation? Normal people will solve graph problems, but I see when you see a scary problem, I see an opportunity. Okay, so I see that everybody will hate this problem. So if I solve this problem, I may be advanced to the World Finals. And that's what I done. so instead of solving nice-looking problem B, again, my idea is so the moral of the story is very simple. So you don't need to love this problem. You should solve them. So problem are not for loving. You take the problem, you solve the problem, you go to the World Finals. That's the plan. Okay, and that's not only for geometry problems. So mostly people hate geometry problems, but not all everybody. So some people hate like combinatorics problem when you need to calculate some strange thing, modular some prime. Okay, it doesn't make sense to calculate this thing, but okay, so you don't need to. You need to like this problem. You need just to know how to solve it. Our second story is about the same contest. I have another story about the same contest. I just remembered it before. So about the last problem of the contest. The thing is that when I first implement the solution, so you have a big, pretty long solution about some geometry involved. Yeah? So, and you submit solution, you get the wrong answer. What you usually do when you have wrong answer in geometry solutions? You think on some big number of tests, you think, okay, maybe I have some precision problems. So maybe I need to rewrite my geometries from floating point numbers to integer numbers to avoid all precision problems. The problem was my solution was already implemented in integers, so I cannot do it. So what I've done, instead, I do something, I do the opposite thing. I rewrite my solution from integers back to floating point numbers. And actually work. I still have no idea why it works. So I probably have some overflow in the middle of my code. I didn't find it yet, but it's okay. Sometimes it happens. Sometimes you do some strange thing to make your code pass the tests. Yep. And my point here is very simple, that if you don't know what to do, just do something. So, especially when you're losing, when you see that you're losing the contest and you still have time, just try to do something, okay? It's always better, if you do nothing, your score will not improve. That's the point. Okay, these are 2 stories from my past. Now let's go to the tips. So I actually copied this part from my Dwerg presentation. So if you're from Dwerg, sorry, you already saw this, but I will repeat it because I think it's important. So first tips are about your teamwork. So team communication is very important because you have 3 people in the same team. You solve the same problems. Some beginner teams try to split problems among them and every person solve their own problem. It works for the simple problems. It doesn't work for complicated problems. For complicated problems, it's actually usually thing is that problem involves several ideas and you need to find these ideas. And you have 3 people that one person may find one idea, another person will find another idea, then you combine these ideas, get your solution. Happens all the time. Yeah. So in one of the contests not so long ago, we had some problem and one of my teammates said, okay, we need to split objects into groups and minimize something. Maybe it is a minimal cut problem. And nobody had any idea why it's problem minimal cut, but then we have some direction to think. And then at some point, another team member found what minimal cut you actually need to find. So it happens. So if you have any idea that nobody said aloud, just say it aloud. Maybe someone else will follow and find the solution. This is mostly about time management. So especially in beginning teams. So it usually happens. Always happens, even in my teams. Sometimes that several people are thinking about the same solution for the same problem. Happens all the time. Just keep track of what everybody in your team is doing. So you know what problems are already solved, what problems are not solved, what you plan to solve, what you plan to do next, and so on. It's a very simple tip. So hard problems need a lot of time to solve. Yeah? So if you first spend all your time solving easy problems, then in the end you will end up with half an hour and no idea about what the last problem was. So start doing it in the beginning. So start by reading all the problems first, and then your brain starts thinking about it in the background. Yeah. So maybe by the middle of the contest, you have at least some ideas about what this problem is. Okay. It's about time management. So again, you have a single computer for your team. It's very important to use it efficiently. So how to use computer efficiently? You basically have some priorities. Top 1 priority is to write the solution. So if you know how to solve some problem and you need time to implement your solution, that's usually the top 1 priority. Second priority is stress testing. I will tell about this every lecture. So stress testing is very important. If you don't do stress testing, start doing it now. So it's one of the most important things in the programming competitions. So I will talk about stress. I have another slide about stress testing because it's that important. If you have no solution to implement and you have no solution to stress, then try to do something. You use your computer. If you have any hypothesis, if you think, okay, maybe solution always exists, or maybe solution always exists if number n is even, something like this. Yes, you think about maybe his hypothesis is true. Just check it. Just again, write a stress test for your hypothesis, not for your solution, for your hypothesis. Check if it is correct. Maybe it's not correct, so you're thinking in the wrong direction. Yeah? Okay, last is debugging. So try to not debug using the computer. Usually it's the least prioritized task. Usually you can do debug on the paper. If you have nothing to do on the computer, then you go debug on the computer. But okay, try to do something else, something more important. Stress testing. So stress testing is again very simple. I'll repeat it again. Stress testing is the most important part. So what you do, you have a solution, you have no idea why it doesn't work. So you send a solution, you get a wrong answer, or you have runtime error, and you have no idea why. You have no test. When you have no test, you cannot debug. Okay? So what you do, you want to find the test when your solution doesn't work. So instead of just reading your problem or your solution over and over again, you may do a very simple thing. You write a very stupid solution. Try to make it as stupid as possible. So you don't make it. So I've done it several times when I have the same bug and stupid solution when it's a normal solution. Don't do it. Then you write some simple generator of the test. I usually do it in Python because it's faster for me. But you pick your own test. And then you just run your solutions over and over again, compare the results. Sometimes, if you have runtime error, for example, you don't need trace. You just run your solution until you get runtime. You should just check that your solution that doesn't fail when you run it. Yeah. Very powerful technique. Okay, we do it almost every contest, and actually several times per contest usually. So every time we have. That's why I push Igor every time to write a stress test when he gets wrong answer. So you do it. I usually do it even before I read my solution. So I get wrong answer. I get okay. It's easy to write a stress test. Let's write a stress test. Then we will find the bug. Whew, again, I was stressed. And in the end, I have several small tricks. So first trick is very simple. So sometimes people submit solutions, then wait for the outcome, and then get wrong answer, and then print solution to find the bugs. You can remove this 5-minute delay. So in the beginning of the contest, maybe less. In the end, maybe like 2 minutes. Okay, but you don't need this delay. You submit a solution, immediately send it to printer. Yeah. If you get wrong answer, then you have to print out. Yeah. Second is very simple. It's mostly for the pro teams. I don't know. So at some level, you get to the point when you solve all the problems, but the computer is busy. So you don't. So like the bottleneck of your performance is your computer. So what you can do, you can prepare before you go to the computer. So you solve the problems, but before you go to the computer, you write your solution on paper. Look like. Sometimes I write just the lines of code. So it's faster for you to implement a solution when you go to the computer. When you finally get computer time, you can implement your solutions in much faster when you already have them write it on the paper. Oh, that's my friend. So people stopped doing it at some point. I don't know why. It was a thing when I was young, but then people just stopped doing it. We don't do it because we don't care about penalty time usually. Yeah, we decide we will not care about penalty time in our competitions, but you should care about the penalty time. Yeah. So what is the idea again? So when you submit a solution, you get very small number of information. So if you have like wrong answer or okay, it will give you one bit. So it's not very accurate. Okay, I understand. It's not how information theory works, but again, stay with me. So the idea is to get more information for every submit. So when you have wrong submit, so you submit your solution, you have wrong answer. This wrong answer doesn't give you a lot of information. It says your solution is not correct. On some tests, it's not working. What part of your solution is not working, you don't know. So you may mark different parts of your program with different outcomes. So you may put something like this to get runtime error, put something like this to make time limit. And then, depending on what outcome you get, you know which part of your program doesn't work. For example, you need to construct some sequence of moves that produces something. And you make not more than 1,000 moves. Yeah? So you make assert that if you have more than 1,000 moves, you do one outcome. If your sequence, if you make invalid move, you make another outcome. If your sequence of moves doesn't produce the desired outcome, then you have it second. So you mark several possible problems with several possible outcomes. So you have more information for every submit. Very simple problem. Yeah, and the most important advice, again, from all this lecture, again, it's like, the most important advice I can give you is actually just to have fun. Okay, it looks silly, but again, this is a, all this event is mostly to to have fun. So yes, we have some prizes. Yes, we have some of you are well advanced world finance and so on. So you have reasons to have a good performance. But if you don't have fun while having good performance, it doesn't make sense. So it doesn't make sense to take part in all these competitions if you don't make fun out of it. Yeah. So try to make fun. Try to find new friends. You have a lot of beautiful people here. So try to make new friends. Try to have fun solving problems and so on. Okay? That's all from me. Thank you. We have some more time to talk about our internship program. Julia, okay. So I pass the floor to Julia to talk about our internship program.
Просто нажимать forward. А ты откроешь? У тебя есть? Окей, просто стрелочка, да? Okay. Hi everyone. It's very nice to see you all. Some of you see you all again. My name is Julia. I coordinate internships at JetBrains, and I just want to take a couple of minutes to tell you a bit about them. And then I'll let you all go because we all understand that 90% of your brain is now taken up by problem solving and 10 maybe by snacks that are coming up. So super fast. So this is a portfolio of JetBrains products. I'm sure I'm missing something, but I'm not going to go into detail about what we do, what products we have. I'm just showing you this to give you an idea of the scope and variety of topics and teams you could get into for your internship. You can see we have the huge Kotlin team, and I don't even mention our research teams on this slide, which we also have. They don't make products, they just do software engineering related research, machine learning, AI, stuff like that. We also have a lot of internships in these areas. So just a couple of numbers about our company. We now have 12 offices in Europe, and a couple of them are in America and China. And we also have a new entity in Poland. So we can also hire in Poland, which is super awesome. And just a couple of numbers about how many licenses, free student licenses, and free teacher licenses we give out. This slide is just to illustrate where our offices are. The Poland is not there yet because we don't have an official office open there yet, but we are working on that. I hope all of you know, but just in case, if you guys don't, scan this QR code to get your free student all products pack, and we also have a rather significant discount for recent graduates. So if some of you are graduating soon, don't forget about that. And finally, we come to internships. The thing I usually like to mention when I talk about internships at JetBrains is that they are project-based. So when you apply for an internship, you get to choose which team, which project you apply to. So you already sort of have an idea of like what skills are necessary for this project. Maybe it's a project that you were like dreaming of working on, and you apply for that particular thing, and you're not going to be like, given a project after you're selected. Also, we offer flexible timing, flexible working hours, so it could be like part-time, full-time. It could start this summer, it could start in the fall, it could start next summer. That's all discussable. And so our next batch of open internship projects will be available from April 3rd to May 5th, 2024. During this time, you can apply, and an application consists of doing the test tasks for each project you choose. And just follow these steps to apply. I'm sure we'll make these slides available, but essentially you just need to go to the website, internshipjetbrains.com, fill out your profile, and that's a very important step because there will be a check mark you have to check that you are an ICPC participant, and this will allow you to view a list of projects that are available for ICPC participants because we don't publish them to the whole world. And so they will be, the full list will be available on this website on April 3rd. And that's it from me. Thank you for listening. Good luck to you all. And a thing I always like to say is that the fact that you guys are here, even just before the contest, is already a big win in my book at least. So congratulations and good luck.
So, how are you doing now? Are you excited after all of these wonderful presentations? Did you learn something new? Yeah! Do you have any questions to any of our speakers or to me? Do you have any questions? Well, we can also chat later. Also, remember at the beginning, I've suggested you to take a selfie with some of the folks here, including the founder of the ICPC, Bill Poucher, and he's right there behind you. So let's give a big round of applause. As I mentioned, we have some fun stuff. Actually, every sponsor prepared some really nice games. So we'll have this chill zone. Now it's open. There are plenty of games, plenty of prizes, plenty of good coffee. I know you all want a coffee, so I'll not take much of your time. And it will also be available after the trial contest, after the rehearsals. Like once you finish the contest, maybe it's too early, you know, for you to go to a hotel and you want to have some other snacks and coffee. So this area will be open. So after questions and answers session, you can also come there and the games will be there until late night. Yeah, and just one word for Professor Poucher.
Have fun and thank you, JetBrains. And of course, and Huawei. But absolutely. And Jane Street and Pineley. There's and Citadel that's not here. Okay. Of course, why? Because the ICPC, okay, to shine the light, need and embrace the leaders in industry and in community. And that's what allows us to have global reach and to be of great service to the universities of the world. We are a creature of them, and our focus is on you. We simply want you to be equipped, energized, and able to build on our strengths and not repeat some of the other stuff. So anyway, thank you very much.
See you on the first floor. We will be there. So if you want to chat, let's meet on the first floor right now. Yeah? Have a great day. There is some announcement.
Yes, and we have 15 minutes break, so after 15 minutes there will be the contest organization notes from Chief Judge.